So, I am going to introduce one more question. So, I have to point out that these questions have been borrowed from a source which is very well known, and that is the MIT OpenCourseware, because they have some standard questions which are worth solving. The solutions are mine, but the questions are theirs. So, but I hope you will enjoy them because I found them very exciting. Okay, so in this problem, the phenomenon of molecular adsorption is being considered. So, molecular adsorption is basically the situation where molecules stick to a metal surface, and so as a result, see when they stick to the metal surface and the molecules have a finite size. So, for example, in this case, we think of a diatomic molecule which has 2 atoms and a bond length in between. So, when they are stuck to the, you can stick a molecule to the metal surface in one of 3 ways. So, either you can, so let me draw a picture of that. So, imagine that this is the metal surface. So, you can have a molecule that is stuck like this, or you can have a molecule. So, this is the diatomic molecule. So, you have 2 atoms here, and this is the bond length, and this is the metal surface. Okay. So, this is the metal surface and this is the diatomic molecule. So, now you can the diatomic molecule can stand upright, or it can lie down flat on the surface, but then this is a kind of a metal surface which prevents the orientation of this molecule to be anything other than these 2 possibilities. So, then the metal does not allow this molecule to just randomly orient itself when it is lying flat. So, it has to be either this or this. So, there are 3 possibilities, but then the energy cost associated. So, then if the molecule is lying flat, the energy for lying flat is 0, but then the energy for standing upright is positive. So, it costs energy to stand upright, but it costs no energy to lie down, except that you are only allowed to lie down along say 2 of the axes, which we think of as x and y axes. Okay, and this is the z axis. So, let us get back to the questions. So, the question asks is how many microstates have the smallest value of energy. So, imagine that there are n such diatomic molecules, and they are asking what is the how many microstates have the smallest value of energy. So, clearly the energy is smallest when all the molecules are lying flat on the surface. So, when all the molecules are lying flat on the surface, so you have to ask yourself how many ways are there to ensure that all the n molecules are lying flat on the surface. So, keep in mind that each molecule can either lie along the x axis or y axis when they are lying flat on the surface. So, for each molecule there are 2 possibilities for lying flat on the surface. So, for n molecules the number of possibilities is 2 raised to n, and the energy is 0. So, if the energy is 0, so this is epsilon. So, you should not confuse my handwriting. This is epsilon, this is capital E. So, this is Latin, that is Greek. So, so you see the number of ways in which you can, the number of microstates when the molecules are lying flat on the surface is 2 raised to n. So, the other question they are asking is what is the largest microstate energy. So, the largest energy is achieved when all the molecules stand upright. So, when all the molecules stand upright, then clearly that is when the energy is largest, and the largest energy is n times epsilon, and the number of ways in which you can achieve that is clearly there is only one way, that is all of the molecules just stand upright, and that is all there is to it. So, so you have this situation where this is 1 and that is the end of story. So, the largest energy is n times epsilon, and there is only one way of achieving that. So, that is the answer to part A. So, what is part B? Part B says, so instead of largest or smallest energies, So, imagine there is something in between, there is some energy E which is in between the largest and smallest energies, then you are asked to calculate the number of microstates. So, the number of microstates are now going to be 2 raised to n parallel. So, this is the number of molecules that are lying parallel to the surface. So, I am going to define n parallel as the number of molecules parallel to surface, whereas n epsilon is the number of molecules perpendicular to surface. So, n epsilon plus n parallel is n, which is fixed. So, capital N is fixed. So, the general case will involve 2 raised to so if the n parallel number of molecules lying flat. So, it is 2 raised to n for the number of ways in which you can rearrange those molecules. So, remember that each molecule is distinct. So, they are all labeled. So, every molecule is different and you know which molecule is which. So, if you decide that there are n parallel molecules lying flat, then you can choose one of them to be along the x or y. So, there are 2 possibilities for each molecule, and remember that the n parallel number of molecules. So, the total number of ways in which you can ensure that the n parallel number of molecules are lying flat is 2 raised to n parallel. But then remember that all you are given is that you are given a capital N number of molecules, but then nobody is forcing you to select a particular set of n parallel molecules to lie flat. So, you have to count the number of ways in which you can select which molecules you have decided to make upright and which of them you have decided to allow them to lie flat. So, now imagine that so if you decide that n epsilon is the number of molecules that are upright, then the number of ways in which you can select n epsilon number of molecules to remain upright from a collection of n molecules is clearly n factorial over n epsilon factorial times n minus n epsilon factorial, which is n parallel factorial basically. So, now so this is the full story of the entropy or rather the number of microstates. So, remember that the energy of the system is epsilon times the number of upright molecules, because the number of the energy of the molecules that are lying flat is 0. So, you just have to count the energy. So, you just have to count how many upright molecules there are, and each upright molecules contributes an energy epsilon. So, it is epsilon times n epsilon is the total energy of the system. So, this also can be written as n minus n epsilon. So, you see the total number of microstates is now expressed completely in terms of the energy of the system and the total number of molecules. So, that is what it is. So, okay, so that is the answer to part B. Well, sort of, because I am also asked to find the entropy, and you know what it is. It is e raised to s E n is nothing but omega E n. So, it is a log of omega is just the entropy. All right. So, next part. So, next part says calculate the heat capacity, but before I think this is jumping the gun. So, I am going to first calculate the canonical partition function. So, remember what canonical partition function is. So, here we have assumed that the total energy is fixed. So, but in the canonical formalism, these molecules, so this metal surface and the molecules are in contact with some environment, a heat reservoir. So, the energy can flow in and out of the system, and then they come to an equilibrium, and when they come to an equilibrium, the temperatures equalize. So, it is the temperature which equalizes. So, I am going to have to study the canonical formalism. So, the canonical formalism is basically described in this fashion. So, you take the energy which is so the canonical partition function is is basically you sum over all the energies. Okay. So, what I have to do now is to calculate the canonical partition function. So, the canonical partition function is basically given by this formula. So, it relates the so I am trading the energy for temperature, and this is how you do it. So, you write the canonical partition function in this fashion, and so now remember that I have already told you what this is. So, this is basically instead of, so remember that the energy is just proportional to the number of upright molecules. So, so instead of summing over energies, I might as well sum over the number of upright molecules. So, you can have a situation where there are no upright molecules, all of them are lying flat, or you can have the other extreme where all the molecules are upright. So, I have to sum over all the intermediate stages as well. So, starting from one extreme to the other. So, so this is what it is, and I have to substitute the number of microstates here. So, so now, so this is what this is. Now, remember that. So, you might be wondering how do I do this? So, summation. So, remember that so finally, this is going to be after summation, this is going to just be a function of the beta, which is inverse temperature, and the total number of particles. So, this summation looks complicated, except that when you realize that there is something called the binomial expansion. So, if you remember that this is nothing but a raised to n times b raised to n minus n epsilon times n factorial over n minus n epsilon factorial. So, n epsilon goes to 0 to n. So, this is the binomial expansion that you are all aware of. So, all I have to do is compare this with this, and you will see that this is easily written as, so this is 2. So, I can identify b with 2, okay, and a with this one. So, if I identify b with 2 and a with e raised to minus beta epsilon, and this is what that is. So, just from binomial expansion, you know that this is my partition function. So, now that I have got the canonical partition function, I can go ahead and calculate the average energy, which is nothing but d by d beta of the log of the canonical partition function. So, this is going to come out as e raised to minus beta epsilon over 2 plus e raised to minus beta epsilon times n epsilon. Okay. So, that is going to be p times n epsilon. Okay. And p is e raised to minus beta epsilon over 2 plus e raised to. So, this is the probability of for a molecule to remain upright. So, p is the probability that the molecule is upright. So, you see that there are 3 possibilities. So, this is so the molecule is upright is this. So, this is identical to well, I can put a p upright there. So, this is p upright, but then there is also the p flat. So, the p flat, the probability that is flat is 2 divided by 2 plus e raised to minus beta epsilon. So, the 2 is because it is 1 plus 1. So, it is either in the x direction or the y direction. So, this is also the probability that it is x, y, then there is the energy is 0. So, it is e raised to minus 0, e raised to minus 0, then e raised to minus beta epsilon. So, these are the 3. I mean, if these energies were there, it would be, so actually this is nothing but e raised to minus beta 0 plus e raised to minus beta 0 plus e raised to minus beta epsilon. So, x direction, y direction, no energy, epsilon energy when it is upright. So, that is what it is. So, and the heat capacity is defined as the rate of one can work this out, and this comes out as 2 times e raised to beta mu beta epsilon times n times beta epsilon square over 1 plus 2 times e raised to beta epsilon squared. So, that is going to be my specific heat at finite temperature. And now you can ask yourself various interesting questions. What is the low temperatures specific heat? So, when temperature is very low, you can expect beta to be very large. So, when beta is very large, you will see that it is going to be exponentially suppressed. So, this is going to be large, and so it is going to, the specific heat is going to turn to 0 quickly. Okay. So, that is because you see at very low temperatures, what is going to happen is that the system is going to be in the ground state, and then you see you will need an enormous amount of energy to even kick out a molecule and make it upright. So, it is kind of the specific heat is going to be 0. So, it is you won't be able to change the energy by changing temperature when you are at very low temperatures, because so it is kind of energetically unfavorable for that. So, that is the reason why the specific heat tends to 0. So, now at very large temperatures beta is 0. So, when beta is 0 at very large temperatures, what happens is that you get a situation which is called the equipartition of energy. So, that means all the degrees of freedom share the energy equally. So, you see that in this problem there are 3 degrees of freedom. So, the one is the x direction, the other is y direction, and the third is the upright, which is the sz direction. So, at very high temperatures, so it kind of becomes democratic in the sense that temperature overwhelms the energy scales like epsilon in the problem. So, the system kind of ignores the presence of this energy scale epsilon and kind of evenly distributes its energy into all the different degrees of freedom. So, even though energetically the upright is less favored, but the temperature is so high that it kind of overwhelms that bias and becomes kind of uniform over all the degrees of freedom. So, as a result, so even the formula itself tells you that when beta tends to 0, which is high temperature, so you see this is going to basically, okay. So, I mean not the specific heat, I am interested in the total energy. Yeah. So, when beta tends to 0, yeah, I am talking about this. So, when beta tends to 0, this becomes 1/3. So, this becomes the probability of it being upright is 1/3. The probability of it being on the x axis is 1/3. The probability of it being along the y axis is 1/3. So, they are all equal. So, as a result, the maximum energy that the system can have is when at very high temperature is at when the system is at very high temperatures, and the maximum energy is 1/3 times n epsilon, because there is when it is lying flat, the energy is 0. So, it is going to be 1/3 times and this is the maximum energy the system can have at positive temperatures. Okay, so, that is the question they had asked. Yeah, so that is more or less the end of this problem. So, it is an interesting problem because it teaches you what specific heat is and how to take a problem description and how to relate it to the concepts that we have learned in this course. So, the next problem is related to oxygen molecule. So, an oxygen molecule is by and large uninteresting. It is just a molecule which has some kinetic energy, and it's just runs around in a box. If you just trap oxygen molecules in a box, it's just just moves around and bounces off the walls. But the only interesting thing about the oxygen molecule is that it has an intrinsic magnetic moment which it behaves like a spin 1 object. So, that means the magnetic moment is quantized, and it is so its projection can be either minus h bar 0 or plus h bar. So, these are the 3 possible values of the spin, and the Hamiltonian for such an ideal gas of n molecules can be written like this. So, the question here is to calculate the partition function for this gas. So, you can see that because there is no interrelation between the spin degrees of freedom and the kinetic energy. So, you can study this problem separately. So, there is a magnetic field which is coupling, so there is an applied magnetic field which couples to the intrinsic spin there. So, there is going to be diamagnetism. So, if you remember, that is what we said, but we are going to ignore all those aspects because so that is the uninteresting part of it. So, that is well understood. So, the problem is that we want to focus on this. In any case, it is a homework problem. So, it says treat the kinetic part using classical physics, and this is quantum clearly because it's either minus 1 0 or plus 1. And so, the rest of the questions are this: what is the probability for the z component of the spin to take one or the other values at some temperature. So, we want to calculate the canonical partition function and answer this question. So, then find the average magnetic moment of the gas, and then find the 0 field susceptibility. So, so let us see if we can answer this. So, I am going to ignore the kinetic part of it because that is the classical ideal gas partition function. So, it just decomposes into 2 pieces. So, I am going to write this Z T and V B as Z T and V 0, that means B equal to 0, okay, times e raised to minus, or in this case because there is a minus already, e raised to minus beta h. So, it is beta mu b sigma I equals 1 to n s I z trace of that. So, that is what that is. Okay. So, this is b equal to 0. So, the only thing interesting is this. So, I will have to trace out this and answer the question. So, let us start answering. So, what is the answer to that? That is Z equals Z 0, this is the classical ideal gas, classical ideal gas times 1 plus e raised to beta mu b, 1 plus e raised to beta mu b plus e raised to minus beta mu b raised to nth power. Okay. So, trace means you sum over all the possible values. So, there can be 3 values 0, minus 1 or plus 1. So, when it is 0 it is 1, so it is plus 1, it is this, minus 1 is that. So, this is going to be my answer, and so that is my partition function. So, what is the probability that the value of z is say one or the other value? So, the probability that it is 0 is 1 divided by 1 plus e raised to beta mu b plus e raised to minus beta mu b. Okay. So, this is the probability that it's the spin projection is 1 as z is as z is 0, this is the probability. The probability that the as z is 1 is, so remember when as z is 1 it is plus e raised to beta mu. So, it is e raised to beta mu b divided by 1 plus e raised to beta mu b plus e raised to minus beta mu b. So, lastly the probability that it is minus 1, it is e raised to minus beta mu b over 1 plus e raised to beta mu b plus e raised to minus beta mu b. So, you see, if you put them all together, you get probability is conserved. Okay. So, this is the probability that the spin projection is at a given temperature. So, the probability that the spin projection is 0, probability spin projection is 1, probability is it's minus 1, put them all together, it's 1. So, this is the probability that a given particle has that kind of spin. So, you work out that what happens at very low temperatures, what do you expect, and what do the formulas say. And so, I mean, we can even think about it right now. So, at very low temperatures, what is beta? Beta is very large. So, when beta is very large, so this dominates. So, you see the probability that Sz is 0 is negligible. So, here again when beta is very large, the probability that it's minus 1 is even more negligible, but then the probability that Sz is 1 is close to 1. So, in other words, when beta tends to infinity, which is low temperatures, at very low temperatures, this is more or less 0, this is more or less 0, this is more or less 1. Okay, so that means all the spins are parallel to the applied magnetic field, which is what you expect. And at very low temperatures, at very high temperatures, when beta is tends to 0, you expect equipartition. That means you will find that all the probabilities are equal. So, 1/3, 1/3, 1/3. So, that is what you get. Okay. So, when beta tends to 0, you get 1/3, 1/3, 1/3. All right. So, that is fairly obvious. And part C, find the average magnetic moment. So, average magnetic moment is basically the derivative of the partition function with respect to beta times b. So, because if you take beta times b as a parameter and differentiate with respect to that, you will exactly bring down this m, and then so you just have to deal with that. Okay. Yeah. So, I am just going to differentiate with respect to beta b. So, so the answer to part B is average mz is basically beta b with respect to ln z. So, and what is ln z? Ln z is basically n times ln 1 plus e raised to beta mu b plus okay. So, if I differentiate this, I get okay. So, if I differentiate this, I get eta raised to beta mu b. If I differentiate this, I get okay. So, that is my answer. So, so that is the average magnetic moment. So, that is fairly obvious, because see, so look, the spin can be either 0 or minus 1 or plus 1. So, if it is 0, then it does not contribute to the magnetic moment. If it is plus 1, it contributes in this way. This is the probability that it is plus 1, this divided by z, and when it is minus 1, it is minus mu. So, the moment is plus mu. If it is 1, it is minus mu. If it is minus 1 and it is minus 1, the probability is that. So, it is just what the moment is times the probability. So, this is basically p0 times 0 plus p1 times mu plus p minus 1 times minus mu. So, that is what that is, times n. All right. So, that is the average magnetic moment, okay, per unit volume. If you want, divide by the density, So, that is going to be the density of atoms, density of oxygen molecules. So find the susceptibility at 0 field. So, susceptibility basically means that you apply a small field, apply a small magnetic field, and you magnetize the molecule slightly. So, the magnetization is proportional to the applied magnetic field. So the question is, what does that become? So, psi becomes d by d b. So, you see most of that look when b is 0, magnetic moment is also 0, because there will be mu minus mu. So, that means if you do a Taylor series, clearly the leading term comes from here. So actually, so you might as well think of this as 0. So, it's mu n by 3 times twice beta mu b is the leading term, right. So, and if I differentiate with respect to b, this goes away. So, that is the answer. So, it is 2/3 mu n times 2/3 mu into 1 by t. Beta is 1 by t. 2/3 into n, so mu squared, mu squared. So, 2/3 n into 2/3 into mu squared times 1 by t. So, this is basically Curie law. So, it is c by t. So the Curie constant is n times 2/3 mu squared. So, the 0 field susceptibility is inversely related to temperature. Okay, I am going to stop here, and we will discuss the other problems next time.